Hello everyone, and welcome to this new section in which we'll look at different ways of creating models other than the sequential API which we've seen so far. In this section, we'll look at the functional API, we'll look at building callable models, we'll look at building model via subclassing, we'll also look at building our own custom layers. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Previously in this course, we said that there are three ways in which models are built in TensorFlow. That is, the sequential API, using the functional API, and then finally model subclassing. As of this point, we have been using the sequential API, as you could see right here. Now, you may ask yourself, why do we need to use a different method in creating TensorFlow models when so far we've achieved close to 99% train accuracy and around 95% test accuracy? Now, as you may have noticed, so far all the models we've been building have taken up this kind of structure where we have an input, we have the first layer, the next layer, which has been stacked in this sequential manner right up to this very last layer here, and then we have the output. So the question we could ask ourselves is, what if we have a model which takes in, say, 2 inputs and has 3 outputs? These kinds of models are very popular in deep learning, and we shall look at them subsequently. But before getting there, you could just imagine a problem where instead of classifying whether we have a non-parasitic or a parasitic cell, we want to know the exact position of that parasitic cell, or in general that cell in the image. You would find that you would have one output which classifies whether it's a parasitic or not. So we have this first output, parasitic or uninfected, and then this other output which gives us the position of the cell, or the exact position of the cell in the image. So here we see already how we could get 2 outputs from this. Let's take this third output out. So here we see we could have, let's even take this one. So here we have this 1 output, 2 outputs model. And with a sequential API, we can't really do this. So that's why working with a functional API is very important. The next point is, we'll be able to create more complex models with the functional API. So there is this model known as the ResNet, which is very popular in deep learning deep learning for computer vision. Now, a ResNet-like structure will look like this. We have this layer, this outputs have been passed into this next layer, and then we have the outputs of this, which are going to be concatenated with these outputs, and then after this concatenation, we are going to pass this to the next layer right here. So if we want to add this layer, we could have a layer here and have that. So as we're saying, we take this output and then concatenate it with this next output before passing to this next layer. And so those kinds of structures or those kinds of models could not be built with the sequential API, and hence the need for the functional API. And then the last reason why we are going to be using the functional API is the fact that we could use shared layers. With shared layers, we could have a layer or a particular layer in our model which has already a predefined way of encoding information. So when we pass information, let's say we have this input, let's say input 1. When we pass this input 1, this layer right here, or this encoder, produces an output which is going to be different from when we pass in another input, I2. But the way it produces its outputs is in a very thoughtful manner. So we could have I1, I2, I3, which all share this layer, and then we have other layers of the model which follow on. That said, we'll look at how to create the functional API. So here we have the sequential, and then just below we're going to create this functional API. Before starting with the creation, we are going to import some classes. So we'll start by importing the input class right here, which is a layer. We import input, and then we have from TensorFlow Keras layer, or rather models, we're going to import model. So we import the model right here, and we import the input. We run this, that should be fine. We now have this func input, since we're using the functional API, just a way of calling that. We have the func input, and then we have input, which we just called, and this takes in the shape. So here we're going to copy this exact shape we use in the sequential API. We have the shape right here. There we go. We copy that shape, and then we reuse it here in creating this input layer. So here we have that, and then we have your shape. So we've had the shape. At this point, you could start stacking up all these different layers we had stacked up in the sequential, or with this when we're using the sequential API. We started with this here, this conv2d, right up to this dense layer. So there we go. We're just gonna make use of this. So we copy that, and then we are gonna paste this out right here. Now, first things first, we have an output. So first things, we have this layer, that's we have this conv2d, which we've defined, and then we pass in the output from this input layer. So here we have this func input. We copy that, and then we pass this into this conv layer right here. Now, once we pass this into this conv layer, we have an output, and that output is this x. And then you should guess that right. We pass this x into this batch norm layer. So here we have x, as you could see, and then we have an output of x. There we go. From here, we pass in the x into the max pool 2D layer. So we have this, we cut that, and then we have this x right here. So we'll just repeat this same process right up to the end, and there we go. You see that we haven't done much changes as compared with the sequential API. So that's it. We pass in this input right here. We have x, we pass it in, we have this, we pass in, and right up to this end. Now, once we get to the end, we are now going to create the Lunette model from this. So we have Lunette model equal model, which we imported, and then we have the func input. Now here, let's say we have func output. So we pass this last, and then our last output is func output. So we have the input, and then we have the output. So there we go. We can now give it a name. We have name Lunette model. If you look up, we had mistakenly written this right here. So this should be the input image. Here we have our input image, and then we've created a model, Lunette model. And then from here, you could simply do Lunette model.summary. Now you will notice that we should have exactly the same summary as we had with the sequential API. So let's run that and see what we get. Here we have how many parameters? We have 4,668,297 parameters. There we go. You see we have exactly the same number of parameters, the same number of trainable and non-trainable parameters. So basically what we've done here is we've recreated this model we created with a sequential API. Now we've gotten this, we'll see that we'll have to change absolutely nothing from our code. So here we're just gonna compile our model without changing anything. We have the same Lunette model. Now we could also change this. Let's say Lunette func, so you see clearly that we are actually using this functional model right here. So we have this func, there we go, func, and that's it. We could run that, and then we recompile right here. So we are not changing any parts of this. We recompile that, and then we train the model. We are getting this error because of the way we named this model right here. So let's have this LeNet model. That's fine. We recompile and then we run. So that's it. We're training our model. And here is what we get as results. Now, coming back to our model, we'll see that we have this feature extraction unit right here. So this conv layers are responsible for extracting useful features from the images, and then these last layers are responsible for correctly classifying whether the image is parasitic or not. That said, we could build a model known as feature extractor. And so here we'll add this. We have our model feature extractor, which is going to be like similar in construction as what we've done so far. So we just have that copied, and then we have this. But the difference is we are not going to include this final layers right here. We'll only end at this point, and then we'll have as output this here. So this is our functional. Here we'll call this extractor. Let's just say we have this as output. So we have this output, and there we go. So here we have our functional input, and then we have this output. And then here is the feature extractor. So we have our feature extractor model right here. We could do this feature extractor, and then we summarize this. So let's run this and see what we get. So that's it. We have our input, and then we have this output right here. At this point, instead of writing all this we wrote here, we're just gonna call, or let's take from this point. So we have our feature. Let's look at the name. We gave it the name feature extractor model. So here we have feature extractor model. So here's our feature extractor model. See, we take all this off, and then in here we pass in our input. So notice how we're making this model look like a function. So TensorFlow models are callable just like the layers. And as you could see here, this feature extractor model could be seen as a layer, just like the dense layer, the batch num layer, and all other layers. So we've gotten this X from this input, which has been passed in our model. And then from here, you see we pass this X into this flatten, and we have the rest. So that's it. Let's now rerun this again so you could see what we get as output. And as you could see, we get exactly what we expected. We have the same number of parameters, and there is this difference here where we have this feature extractor. So unlike before where we had the conv nets, like the conv2d, batch num, max pooling, and the same, like let's go up here, this is actually the feature extractor. So unlike before where we had this and then this, now it has been replaced with this feature extractor right here. That said, we've just built this model using the functional API, and in subsequent sections we'll build even more complex models using this functional API. Models where we're going to use shared layers, we're going to have multiple inputs, multiple outputs, and models where we're going to have even more complicated model configurations. It's important to note that you could mix up the functional API model creation style with that of the sequential API. So here, instead of creating this, so instead of having this feature extractor created like this, we are going to create it using the sequential API. Let's add that, and then we copy out this from here. Copy out this full model with a sequential API. We paste this out, and we take only the feature extraction part. Here we see we take this off, and then we're left only with this feature extraction part. Now let's call this feature extractor. So feature extractor sequential model. There we go. We paste this out right here, and we're fine. So we have our feature extractor model. We run that. That's okay. Let's take this off. And then we'll just make sure we put exactly the same here. So there we go. We paste it out and we rerun this. You see, we should be able to get exactly the same output. See, we have exactly the same output. And here, instead of our feature extractor model, we have your sequential layer. So that's it. This shows us that we could mix up these different ways of creating models. From this point, we'll look at the model subclassing. So right here we have our model subclassing. There we go. It's important to note that model subclassing permits us to create recursively composable layers and models. Now, what does that mean? This means I could create a layer where its attributes are other layers, and this layer tracks the weights and biases of the sub layers. Before taking an example, let's make this import. So we're gonna import layer from layers. We have TensorFlow.keras.layers. We're gonna import layer. We run that, and then we move on to create our model using the model subclassing. Now that's set, we have this feature, our feature extractor. So we have feature extractor right here, and then this inherits from layer. So it inherits from TensorFlow layer, and then we have an init method and followed by a call method. So that's it. Now let's use the right syntax. Here is a class, here is a method, init method. There we go. You could always check on our free course on Python programming in case you're not versed with all this syntax. So that's it. We've had that. And now, just like the way we did when we were creating this feature extractor, let's go back to our feature extractor with a functional API. Actually, here you'll see, let's copy this out and then get back to our model subclassing. So that's it. Here, let's just put this down here. And then we have the super feature extractor. There we go, that init. So that's it. Now that we have defined this, we could now go ahead and use this layers as the attribute for this feature extractor layer. So there we go. We have this here. We have our conf, the self.conf1, which is this conf2d right here. So we take all this off and just place it here, and then from here we have the batch1, which is this batch norm layer right here. Take this and then place it right here. We have the max pool 2d, take that off. We have self.pool1. There we go. So that's it, and then we just repeat this process. So we could have the self.conf2 rather, so conf2, and then we just take up this parameters. Let's take this from here and place it right here. So here, instead of having this, we will just get this, and then the batch normal max pool 2 they remain the same. So that's it for our init method. We now go ahead to build our call method. We have our call method here, which takes this input x, and then here what it does is it permits us call each and every layer we've defined here in this init method. So here we have x equals self. So the value of x is going to change. We're going to pass it through self.conf1, and self.conf1 is going to take in x. This looks similar to the functional API. We have x equals self.batch1. There we go. Batch1, and then we have x equals self dot pool 1, x equals self dot conf 2, x, and then self dot batch 2, and finally we have self dot pool 2. That's it. So now from here we just return x. Also note that we could pass in a parameter, an argument like the training, which can tell us whether to use a given layer or not during the training process. Nonetheless, for now, all this is going to be used during training, so we have that. Now let's take all this off. We run that. There we go. That's run correctly. Now we should be able to build our model. So here we have this Lunet model, which took the feature extractor model from here. Let's just copy this, and then, but before copying that, we have to ensure that we create this here. So we have feature subclassed. So we have our feature subclassed, which is this feature extractor we built right here. So here we have feature extractor we built. So that's it. Now you could always pass this parameters like the number of filters, the kernel size via this. So you could pass this here. You could specify filters and the kernel size. So let's just do that. So let's say filters takes kernel size, strides, and say padding and activation. So we could pass all this here, so that when we get to this point, we don't need to specify all this. So we'll simply take this off. No need to specify all this anymore. Now we have our activation, all that specified. Okay, we could also include the pool size. Let's include the pool size and this strides here. Okay, so let's just say here we're gonna have 2 times the strides, because we will specify the strides to be 1. So let's take this off. Here we're gonna have 2 times the strides, and we've defined here we have the pool size. So let's take this off, and let's take this off rather. Let's get back. So we take this off and take this off. So that's it. We've defined all that, and now we are ready to pass all these values. So we'll just simply copy all those values, and then in here we'll specify the number of filters. So here let's take 8, the kernel size, let's take 3, the number of strides, we have 1, the padding, here is valid, activation, relu, pool size is 2. So that's it. So we've defined all this. Now at this point, let's ensure that we have this times 2. So let's run this now again, and then we have our feature extractor, but we're getting this error. Let's try to understand why and how to solve this error. So there we go. Scrolling, we have this. Now the reason why we have this error is because of the order in which this conf 2D takes its arguments. So if you look at this, I'm trying to get this to come up. Anyway, we just look at the documentation. You see we have filters, kernel size, strides, padding, data format. So you see we have the data format, the dilation rate, groups before the activation. So it's important that we specify that this is filters equal filters, and then here we specify kernel size equal kernel size. If not, it's going to take this to be the data format. So that's it. Strides, padding equal padding, and activation equal activation. So this should be fine now. We run that again. We have this error, but this time around it's for the second conf layer. So let's just redo what we had done here and take this off. Notice filter size times 2. So here we have filters times 2. We try to do the same for the max pool 2D. So here we have pool size equal pool size. That's it. strides, that's fine. And then yeah, we have pool size equal pool size. Okay, so now everything should work fine. We run that, and there we go, everything works fine. So now we've created our layer, our feature subclass layer. We'll now be able to use it in this model right here. So let's copy that and then get back to this. I'll paste this out here, and now here we have our feature subclassed. Let's take all this off, subclassed, and then we could comfortably run this, and we get in this error. Now let's get back to check. We see batch 2. This is an error level batch 2. Now you see here we have this 2. This should be 2, and this should be 2. So that's fine. Let's run that again, and everything works well. So you see it gives us exact same output we expect to get with this feature extractor right here. Then one last thing we could do is, instead of doing this way, let's insert some code. Instead of doing this way, we are going to create a model using this model subclassing method. So here we just, let's copy this out. So we copy that out, and then in here, instead of having layers, so here we're not having a layer, we're having a model. So instead of having layer, we now have model, and then we're gonna define a feature extractor. So our feature extractor now is going to be the feature extractor we've just defined here. So let's go up, and there we go. So we're going to get this feature extractor right here, and then what we do is we put it in here. So let's take all this off. We have all this off. That's now our feature extractor. So we've gotten this feature extractor. That's it. And then once we get X, we're going to pass this through our feature extractor. There we go. Let's take all this off, and we're fine. Now we're done with the feature extraction. We could get the other parts which make up the model, like this flatten, the dense, and the batch norm. So let's take this here. There we go. We are in this model, and let's just copy it. Let's paste it out here. So here we're gonna have this. Also note that we're gonna have feature, or let's say lunette. This is our lunette model. Modify this here. We have lunette model. So that's fine. Now we've gotten this, everything is understood. We now check out this self.flatten equal flatten. And then next we have self.dense1 equal, let's copy this out from here simply. So we have this dense right here, which is our dense 1. There we go. We have our dense. And then we have self.batch1, which is our batch normalization. There we go. Copy this and paste. We move to dense 2 and batch 2. So here we have dense 2, we have batch 2. This is 10 actually, so we have that. And then finally we have this dense layer. So let's take this off. We have the dense layer. Output 1, activation sigmoid. So there's it. We call this dense 3. So that's fine. Everything seems okay. Let's take this off now. And then there we go. We get into our call method. So yeah, we get into this call method. And this call method will basically call all these different layers. So after the feature extraction, notice how we've created this class, and this class makes use of this feature extractor, which was also created using the same model subclassing method. So there we go, we're using this here, and we're actually using it here. So that's it. Now we just make this calls. So we have x equal self.flatten, and then we pass x equal self.dense1, passing x, x x equals self dot batch 1 passing x, and then finally we have this. So there we go, we now return x just as we did previously, and we have our model. So here we have our LeNet model, LeNet subclassed model, and we have this LeNet here, LeNet model. So let's take this off, and there we go. We've just built our model, which when we try to find a summary, so we try to do LeNet subclass.summary, what do we obtain? You see, this model has not yet been built. Build the model first by calling build, or by calling the model on a batch of data. So we're gonna call this model on a batch of data. Right here we're gonna have LeNet subclass, and then we have tf.zeros, and 1 2 2 4 2 2 4 and 3. So let's run this and see what we get. That's fine. So here we have our summary, and then we are ready to compile this model. Here we have LeNet subclassed. So we compile LeNet subclassed, and then we're gonna fit LeNet subclassed, So we feed that, and everything should work fine. Let's take this to just 5 epochs. We can see that we're getting similar results when we compare this with what we have with the functional API and the sequential API. So we now move on to creating custom layers. If you could recall from the previous sections, the way the dense layer is built is such that if we have this as our dense layer, and then we have this input right here, let's call this I, or let's say it's X, we have this input X, then we have a certain M times X plus C. So this M is actually the weights, so it's the weights times X plus the bias B, let's call this B, and then this is now equal our output. So here we have an output of y equals mx plus c. So this simply means if we want to recreate the dense layer, then we have to take this into consideration, or the definition of the layer from scratch into consideration. That said, we could define a neural learn dense. So it's like our custom dense, neural learn dense. It's gonna inherit from layer, and then right here there's a class. So we have this class inherits from layer. Then from here we have our init method, init, and then we have the super. We pass in neural learn dense. There we go. We have that init. So that's it. Now from here, if you had noticed, whenever we're creating a dense layer, like let's come up here, whenever we're creating a dense layer, we generally had to specify at least, because this is by default. This is not by default, but so here we need to pass in this here to specify the number of output units. Now that said, we have to take that into consideration when building our neural net dense layer. So here we have output units. There we go, we have our output units, and then in here we'll define self.output units to be equal output units. So that's it. Now from this point, we're gonna build this layer. In order to build this layer, we have to take into consideration this definition right here. But this definition put out the way it is isn't very clear. Now let's make this, or let's break this up. So you suppose that we have this input of shape batch size by, let's say, number of features. So suppose we have this input. Now what happens here is this input is going to be multiplied by this weights. So it's going to be multiplied by this weight, which happens to be a matrix. Now we take this and multiply by that matrix, and for the multiplication to be valid, we need to ensure that the number of columns we have here matches with the number of rows of this matrix. But then, what are the dimensions of this matrix? We have to note that this matrix has to be defined such that we have a shape of f. This f here must match by the number of output units. So if you want your number of output units, for example, to be 1, then here you should have 1. And that's why when defining the dense layer, we don't need to specify this, as this value is gotten automatically from the number of columns in the inputs. Since if we don't take this, we are going to have an error. So TensorFlow takes this automatically, fits in here, and then collects the input you passed in the dense. So when you specify, when you say you have this dense like this, and then we say, for example, 1 and maybe some activation, then you have that. So let's say we have some activation here. Now once this one gets here, this weights matrix is now defined such that the input you pass into this dense is going to affect the number of rows we have. But then what you pass in as argument here is going to tell us or give us the number of columns we're going to have for this weight matrix right here. So that said, we have f by 1, and then when we multiply this, we're going to have b by 1. So we now understand how we get this output, and then we have plus b by 1. So that's it, where this one comes from the bias. Now once we add this up, we have an output of b by 1, and that's our y. That's the shape of our y. If that's understood, we'll move on to building. So here we have our build method, we have self, and for now let's keep it that way. So there we go, we have this build method, and then we're gonna define our weights. So we have self.weights. Let's specify weights equal that, and then here we're gonna have the self.addWeights method. So this actually comes with this layer class right here. So we're able to call this because we are inheriting from the layer class. So here we have self.addWeight, and then we specify the shape. So guess what? We are gonna have our number of rows, so n rows, which is gonna come from the inputs, and then we are gonna have our number of columns, which is gonna come from those output units you've specified, which you pass in when calling the neural learn dense layer. So here we're gonna have self dot output units, so we get a number of output units. Now how do we obtain this number of input units? We're gonna look at that shortly. For now we have the weights, and then we have that, and then let's go to bias. So we have self.biases and this is also a weight, add weights, and then here we specify just the number of output units since it's one dimensional. So we have output units, there we go. And so at this point we've defined our weight and our bias matrix. This actually weight, just singular. So that's it. Now let's go into call. So we have our call method, which will actually get a job done, and then we have our input. So let's call this input. Let's add an s, or let's say input data, input features. So there we go. So we have that, and then what we're gonna do here is we're gonna return simply the matrix multiplication, as we've seen already, of the weights. So we have self.weights and this input features. We call it's actually the input features times the weights. Like, let's get back to this. Here, if we take the input, we need to take this input times the weights, because if we have the weights times the input, we will have f1 times bf. We call our weights this our weight shape, and then this our input shape. Multiplying this, you see that this isn't always the same, so it's not going to be, it's going to throw an error. And so that's set. What we're going to do is we're going to just simply have input features right here. So that's it, and then we add up the bias. So here we have self dot biases, which is from this one right here. Now the way we're gonna get this number of rows is gonna be easy. Here all we need to do is to specify here that we have the input features shape. We have our input features shape, which is gonna come automatically from this. And then to get the number of rows, what we need to do here is have input features shape, and then we get that last dimension. So let's get back to this. We call here we're having b by f, that's bf, and so here we need the weights needs to be f by the output. And so to get this f, we just need to take the input and then get this last element right here and get this the number of columns we have here. So that's set. We will just have that input features specify this, take this index, and that will be good. So that's how we obtain this value automatically, the number of rows we've been looking for. So now we've gotten this, everything seems fine. Next thing to do is to specify that it's trainable. So we have to specify that these weights are trainable, because in some cases we may want that the weights shouldn't be trainable. So self.trainable equal true. Now this one self here, this is an argument, like it's one of the arguments which have been passed into this add weight method right here. So we just have that, and then here again we have this trainable equal true. Now apart from that, we could randomly initialize our weights and biases. So here we have random normal initialization. That's fine. And then we do same here. So we have our initializer equals random normal. That's good. We now run this. Here's our neural learn dense layer, and then after running this, let's get to integrate this. Let's make it quite simple. We just use our sequential API. So let's get back to this sequential API we had built initially. Copy that, and then we are going to integrate this new dense layer, this neural learn custom dense layer. So there we go, we have that, and then instead of dense layer here we have neural learn custom dense layer. So you see that you can be able to create your own layers with TensorFlow. So that's it. Neural learn. So neural learn dense. Now you see this should throw an error because we don't take into consideration the activation. And so what we could do is we could get back right here and say if the activation is equal relu. So if our activation is equal relu, we'll return this, and then else, let's say elif activation is equal sigmoid, we return that. Oops. Let's get back. We have this, so we're gonna return this. Let's copy this and then paste out right here, and then we have else. We'll do the same. So now let's get into this and see the modifications we're gonna make. There we go. So here we have our relu. In the case of relu, what we wanted to have here is tf.nn.relu of that. So we're gonna pass this in to our relu, and then if the activation is sigmoid, we should have tf.mat.sigmoid. So that's it. There we go, we have that, and then this one we just maintain. So we've modified our code such that we now integrate the activations. There we go. That seems fine. So let's run this and then take this error. So here we have this double equals Python syntax, and then we come down here. Everything seems fine. Let's check this again. Here we're supposed to specify activation. So you're supposed to have activation, and then self.activation equal activation, and then here we have self.activation. We run that again. Looks fine. And then now what we do is we just simply run this. So we run that, and we get in this error right here. To solve this problem, what we're gonna do is we're gonna include the shape here. So we're gonna have shape equal that, and then shape equal this. Let's rerun that, and we should have no error again. Oh yeah, we can't set the attributes weights, likely because it conflicts with an existing read-only property of the object. So right here, instead of using weights, we're just gonna say W. So we have the W, and then right here we should have W. Now since we don't want to repeat this over, what we just say here, we have pre-output. So we have our pre-output, which is this here, and paste that out, and then here we have W. Right here we have B. That's it. And now we have if this, then we pass the pre-output, and we do the same right here. So we have just a pre-output before the activation. Now here we just have pre-output actually, so we just have pre-output. We take that off. Now running this should be fine. So let's run that and see what we get. We run this, we run that, and there we go. We have our model, the same exact model we have been building right from the start, but this time around we're using a custom dense layer, which is our neural learn dense layer. Now let's go ahead and compile this model and then train it. Yeah, we've actually maintained this here, so we have to change this name. Here is Linnet model. Let's say Linnet custom. Custom model. Yeah, okay, we copy that. We have our Linnet custom model. Let's have it here. There we go. We run it. That's fine. Right here we have Linnet custom. We run that. Here we have Linnet custom. We run that, and then let's check out. As you can see with the training, there's a slight difference in the lost values and accuracy we're getting for this first epoch, and most probably this is coming from this random normal initialization we've chosen here. As with the standard dense layer, which you could see here, this kernel initialization or the weight initialization is using this Gloro uniform, and the bias initialization is the zeros. So here we have all zeros for the biases, and then here we use the Gloro uniform method. So here, as you could see, this isn't performing as well as what we had previously. But scrolling up, there is this error. So here was meant to be sigmoid. So let's stop this. Let's interrupt this training, and then get back and run this. So we will run this and compile, and then start with the training again. This time around it looks better. It looks more like what we should expect. So even though we're not using the Gloro initialization method, this training process looks quite similar to what we would have had in the case of the Gloro initialization method, which is used with a standard dense layer. And here is what we get after training for over 5 epochs. Thank you for getting up to this point, and see you next time.